have an exemption sheet posted.
I wish I didn't.
I do not. Okay, so hey, listen, everybody. If you're joining me from home, I'm going to start to go over the study guide real quick. This semester test will be over everything from January. So let me see if I can present my screen here. But everything since January, so going all the way back to like stoichiometry. Study guide should be on Google Classroom now, so you'll just need to print it off. If you cannot print it off, I can certainly get you a copy to the office. You'll just need to stop by and pick one up if you prefer to have a printout. Okay. All right. So here we go. Let's start looking at this. Okay. So starting with number 1. And we're going to try to rip through these pretty quickly today. And then I'm going to do a separate video with just the math problems. But starting with number 2 here, chemical reactions are similar to nuclear. So you're picking all the things that are the same. They both will undergo energy changes, and they're both going to produce new substances. Okay. Number 3, small massless negatively charged particles. That's going to be electrons is what it's talking about. Shh, guys, listen. Beta particles is what you're looking at there. Moving right along. Number 4. The reaction that occurs in our sun and produces helium, that's called fusion. Okay, nuclear fusion. Number 5, fission is responsible for which of the following? We know that's going to be atomic bombs for sure and power plants. That's fission. Okay, number 6, which particle is emitted in the alpha decay of americium-241? So you would have to find americium-241 on the chart and think, what is alpha decay? So we know it's going to produce a helium particle if it's alpha decay plus another nuclide, okay? But already, if you look at this, the only choices here are going to be electron, gamma, hydrogen, or helium. The one that you're looking for is helium, okay? And then you would just use the periodic table to figure out this other part. Now, number 7. Okay, what particle is released with the beta decay of iodine-131? And again, this is one of those problems where you're going through a decay process. Iodine-131, you have to come up with the proton number, which that's on the periodic table. So iodine is number 53. Number 53. And it's going to break down to produce, oh, hang on just a second. Hey, Kenyon, the office needs your lock off your locker. So
I don't know the number because I never used it.
Oh, I would just go talk to Denise and see what she wants you to do. Oh, yeah, thanks. Good call. All right. So, so you got iodine. If they're telling you this is beta decay means it's going to be a beta particle, which remember is just an electron. Okay. So if this is a beta particle, the other particle here, because you look to see if beta particle is over here and it's not. So that can't be one of the choices. So it has to be this other particle right here. So in order to do this, remember this side of numbers has to match this side of numbers. So we know this is going to be 131 on top, because 131 and 0. And then -1 plus what number would get us 53? Well, over here on the side, it would have to be 54, because 54 minus 1 would get us 53. So then we just have to figure out which element is number 54. Okay, so number 54 is that one right there, xenon, Xe. So xenon is number 54, and we call this xenon 131, which is that one. Okay. Number 8, what's the purpose of the Manhattan Project? I think you guys were learning about this in world history. Also, the purpose of that project was to create an atomic bomb. Number 9, besides the Tennessee facility, which was used for production, fuel production, what state was the other facility used for research and testing? It was New Mexico, Los Alamos, New Mexico. All right, next. Number 10, select the main two elements used in the creation of Fat Man and Little Boy. Those were the two bombs, right? Okay, so the main two elements that were used in the main production is plutonium and uranium. Next, the Hungarian scientist Szilard drafted a letter that was signed by Einstein that basically informed which U.S. president. So we're talking about which U.S. president was that first letter written to, and it was Roosevelt. Oh, which Roosevelt? It was Franklin, FDR. Okay, number 12, in order to balance a chemical equation, it may be necessary to do what? Well, adjust the coefficients is your best choice. You don't want to do any of those other things. That would be bad. Number 13, people aboard the Titanic that were exposed to extremely cold waters of the Atlantic had no choice or no chance of survival. Why? Okay, well, last week we did some fire bubbles at the beginning of the week, and we talked about the reason why we can coat our hands in water and light our hands on fire is because water has an extremely high specific heat. It can absorb a lot of energy. So it's got to be one of these two middle ones. Okay, we also know that heat flows from areas of high heat to low heat. So if you're looking at these, it says the water has a high specific heat and the cold water went into their body systems. No, that's not true. The water has a high specific heat and the victim's body heat escaped into the cold water. That's your best choice. Okay, that one right there. All right, number 14, would an ice cube melting? So would an ice cube melting be considered endo or exothermic? This would be a nightmare. There we go. All right, so if this is going to go from frozen solid into liquid water, right? What's going to cause that to happen? Well, it's going to have to heat up, right? It's going to have to get heat from somewhere in order to make it melt. So if heat has to go in, which one would that be? That would be endothermic, because heat goes from areas of high heat into cold. Heat would have to flow into the ice cube. So that's your best choice.
Response, please come to the office.
Haber process, we talked about this several weeks ago, is used to create ammonia on a massive scale. Okay. Number 16. Okay, Le Chatelier's principle states what? Well, we talked about Le Chatelier when we were going over chemical equilibrium. And we said that it's basically when you apply stress to a system, the system will shift in the direction to reduce or to correct the change. That's going to be letter C. Number 17, a theory must do what? Should it be tested thoroughly? Yes, it should. It should have already been tested thoroughly. Should it be an idea or explanation supported by evidence? Yes, it has to be. Should it be able to be modified or changed as new evidence is introduced? Yes, it has to be. Should it have only the support of one or two scientists? No, it should have the support of many people in the scientific community. Okay, number 18, a theory that explains a possible origin story for the universe based on the idea that it came from a single point in space, expanded outward, Big Bang. Number 19, which of the following pieces of evidence is not used to support the Big Bang theory? Is it red shifting, pockets of heat, large amounts of hydrogen and helium, or large amounts of carbon and oxygen? We talked about 3 of these. The one we did not talk about was this one, because that's not a piece of evidence they used to support the Big Bang theory. Okay, number 20, Edwin Hubble was a famous scientist. What invention is he most famous for? That would be the Deep Space Telescope. Number 21, as galaxies move away from us, they tend to speed up. Right? 22, what did Wilson and Zayas discover in the 1960s? They actually were the ones that discovered those heat pockets, that cosmic background radiation. 23, aging or dying stars tend to produce elements like what? So we had this big discussion in third hour. Like if you Google this, it will actually give you carbon and iron both as choices. Well, the thing is, though, the one that will be produced right before a star dies is going to be iron, because it takes way more energy to make it, to fuse those elements together to make iron than the iron would give to keep the star alive. So it's iron. 24, if a galaxy is moving towards us, it's considered to be blue shifting. If it's moving towards us, what does that mean? Well, it just means that the wavelengths are being compressed. red shifting, they're being stretched out. If it's blue shifting, then they're being compressed. 25, if you know a galaxy's observed wavelengths, okay, so if you know the observed wavelengths, and if you know the actual, like a reference wavelength, what else would you need to know? What could you calculate first and foremost? That would be redshift. That's the first thing you would need to calculate is the redshift, which, by the way, is Z. Okay. Number 26, the nearest galaxy to ours is this one, Canis Major Dwarf. It's 25,000 light years away. What's its recessional velocity? Now, here's the thing. They're asking us to find V, okay? And they're telling us that it's 25,000 years away, which is D, distance, okay? So then you would have to actually figure out what's its recessional velocity. We had a formula for this, and I think my third hour class wrote it up here. Yeah, they did. We know that if you're trying to find distance, it's velocity over Hubble's constant. And Hubble's constant is this number right here. Hubble's constant is 2.30 times 10 to the negative fifth. So there's our formula, okay? That's the formula. Distance is equal to velocity over Hubble's constant. They're asking you to find velocity, though. How would you get this V to be all by itself? You have to rearrange the formula to where it's going to say V is equal to, and you multiply both sides times Hubble's constant. So velocity is equal to the distance times Hubble's constant. All right, just like that. And if you plug it into your calculator correctly, the answer should have been 0.575 kilometers per second, I believe is what we came up with earlier today. All right. Listen, and this formula, you could write it on your study guide. Yes. Write it on your study guide. You're going to need it. Okay. Number 27, the height of the wave from the origin to the crest. So the height of the wave, if you're looking at a wavelength from the origin point to the crest, so like let's say that this is the origin point. So this right here would be known as its amplitude, the height. Height is amplitude. Okay, 28. If the frequency of a wave increases, what must happen to the wavelength? Well, remember, frequency is with that weird little V, and then wavelength is the upside down Y looking thing. Okay, if frequency goes up, so if they're really close together, the waves are, what happens to the wavelength in order for the wave to maintain a constant speed? Well, if frequency goes up, wavelength is going to go down. They're going to get closer and closer together. Okay. So it's an inverse relationship. Okay, oops. There we go. So if that one goes up, wavelength must go down. It must decrease. So, 29, which parts of the electromagnetic spectrum have longer wavelengths than ultraviolet light? I can't ever do this without thinking about the order. So I always have to think, okay, it's GAX, U, BIMR. So gamma radiation, X-ray, ultraviolet, visible, infrared, microwave, radio. I also make myself some notes. I know that this side is going to be real high frequency. It's going to be real high energy, and it's going to be short wavelengths. This end down here, these are the radio, the harmless radio waves. So low frequency, low energy, and long wavelengths. I always think long and low. Whoops. Okay, long and low. So which part has longer wavelengths? So we want to go in the direction of longer. So we're going to be moving down on this end. And longer than ultraviolet. If ultraviolet is here, it has to be anything from here on out. All of those have longer wavelengths than ultraviolet. So let's check all that apply. It's definitely going to be visible and infrared, not X-ray, definitely microwave, and not gamma. Okay. Number 30, select the following properties that would describe gamma rays. Gamma rays are on this end. Remember, they're really high frequency, high energy. They're very harmful. Okay, so having said that then, these are going to be high frequency, short wavelengths, high energy, and harmful. Okay, all of those things. All right. Number 31, if a radio wave has a frequency, well, listen, I'm going to make a math video, so we're going to come back to that one later. So we'll come back to 31. 32, Isaac Newton used the famous experiment to support his idea that light traveled, how it was a prism experiment, and it travels in straight lines. Okay. 33, which part would be the wavelength? The wavelength, remember, measures the length of a wave, so from crest to crest or trough to trough. So it's definitely not going to be B. This would be your best choice because letter C is measuring cycles per second. So this is frequency. This would be wavelength. So A is your best choice. 34, photoelectric effect supports that light behaves like a particle because if you read through all these, photons will cause electrons to be displaced, assuming the photons are at the right frequency. This is your best choice. Okay, that's why we know it behaves like a particle. Okay, 35.
Miracle Frank, please come to the office.
Einstein said that light does what? He's the guy who put both of those theories together, the wave theory and the particle theory. So he said they have a wave-particle duality. Number 36 is also a math problem. Like I said, we're going to come back and do that one later. 37, which type of radiation travels faster, microwave or X-rays? Neither. They travel at the speed of light. Okay. All right. 38. For the following reaction, which of the changes would cause the system to move in the forward direction or to the right? Okay. If you're wanting it to go this direction, we said that you could do three things. You could either add more of something, specifically, like if you're wanting it to go that direction, you need to add more to this side of that chemical, or you could take something away. And again, if you want it to move in that direction, I would take stuff from this side away. You cause it to become unbalanced, right? So I would take something away from here to make it move in that direction to make more. Number 3, you could adjust temperature, but it really doesn't give us enough information to know how to do that. And number 4, you could adjust pressure if you wanted to. Remember, if you adjust pressure, things will always move to the side. If you want to move it to the side that has, if you increase pressure, it's going to move to the side that has less particles. So if you wanted it to move to this side, you would actually have to decrease the pressure. Okay, because if you increase the pressure, it's going to move this direction because it would want to move it here because you've only got 2 particles. This has 3. All right. So here we go. If we wanted to move this direction, we don't want to increase the pressure because that's going to make it go in the wrong direction. Do we want to take this out? No, you don't want to take this out. Do you want to add more chlorine gas? If you put more chlorine gas on this side, it's just going to shove it that direction. So we don't want to do that. How about if we remove nitrogen monoxide? Yes. Because if you remove it, it's going to have to make more. All right. 39, a system that has no net change of reactants and products during the reaction is said to be what? At equilibrium. Okay. All right, number 40. For the graph, explain what might happen to the surroundings and the enthalpy change you might expect. Okay. This is an endothermic reaction. And remember, endothermic means that heat is going into the system, okay, which means the surrounding should get colder, right? And if it's endothermic, enthalpy should be a positive number. So it should be a positive value. And the surroundings should get cooler because the surroundings are losing heat. Okay. All right, so let's see if we can figure this out. So we're looking for surroundings and enthalpy change. So Surroundings are releasing heat, losing heat. That's true. And enthalpy is greater than 0 positive. That looks right. Okay. And just to double check ourselves. So this one absorbs heat. No, that's not true. Surroundings get warmer. That's not true. Surroundings get cooler. That's true. But here it says it would be negative, so that's not. This is our best choice. Okay. 41 is a math problem. We'll come back to it. Okay. Number 2, covalent bonding. Between two nonmetallic atoms, covalent bonding is an example of what? Okay. If it was intermolecular, that means it would be from molecule to molecule. Okay, if it's intra, that means within a molecule. Okay, so an atom to an atom. Okay, hydrogen bonding and London dispersion, these are both types of this. So your best choice here is that one. Okay, next, the measure of the transfer of energy from areas of hot to cold is known as what? Well, temperature measures movement. Enthalpy is the heat of the reaction. Potential energy has to do with stored up energy and usually height. So heat is your best option. Okay, number 44. If your enthalpy is positive 277, the system would be considered blank and the surroundings would get blank. Well, if this is a positive value, remember, positive indicates that it's endothermic. And if you're talking about surroundings, the surroundings are going to lose heat. They're going to get cooler. So we're looking for endo and cooler, which is that one. Okay. 45. Energy needed to start a reaction to activate it is known as activation energy. Okay. If the energy of the product is less than the energy in the reactants, the energy is considered what? Okay. So if the energy of the products is less than the energy, that means it lost energy. So if you're losing heat in a reaction, it's going to be exo. Heat is released. It goes out. So it should be letter B or the second choice. So 46 is exothermic. Number 47. 47 is going to be, in order for photosynthesis to occur, carbon dioxide and water must react and sunlight must be absorbed. Glucose and oxygen are products. What type of process is photosynthesis? Okay, if energy has to go into the reaction, it's got to be endothermic, okay? So endothermic, but they've got two choices here. And photosynthesis then, it absorbs energy through sunlight. That's true. So the best choice is letter A there. So 47 is endothermic, letter A, or first choice. Number 48. 48, the amount of energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius is known as what? We talked about this when we lit people on fire last week. It's known as specific heat. Okay. All right. So number 48 is specific heat, which is letter C. If you're keeping up with letters. Number 49, if two substances are mixed together, what would you not observe that would indicate that a chemical reaction has occurred? Okay, so we're looking for what would you not observe? Well, precipitation is chemical reaction. If it evaporates over time, that means you're just going from a liquid to a gas phase. So that's just a phase change. Let's check these other ones. If the color changes and if there's a change in energy or heat, those are both indications of chemical reactions. The best choice here is letter B. So number 49 would be letter B if one of them evaporates over time. Number 50 is going to be a math problem we'll come back to in the next video. Number 51, also math, we'll come back. Also math. Number 52, we'll come back. 53, what's meant by actual yield? If you go back to the lab and you do an experiment and you actually produce a product, that's your actual yield. Then you would compare it to something called a theoretical, which is what you calculate with stoichiometry. So an actual yield is the measured amount that you get in the lab of a product produced in a chemical reaction. So number 53, the best answer is letter B, the second one. B, yeah. All right, so number 54, how would you calculate percentage yield? Percentage yield is just going to be actual over theoretical times 100. So that's going to be your last choice, letter D as in dog. So 54 is letter D. 55, why do we balance chemical equations? Which law are we trying to satisfy? It's the law of conservation of mass. So 55 is letter A. 56 is a math problem. And 57, whew, made it. Using what is known about reactants or products to calculate other amounts is known as what? That's called everybody's favorite subject, stoichiometry. All right. We'll do a math video here in just a second. Good luck.
Okay, what was 54? Oh,